Okay, hello, welcome students to today's lecture for the course MA412 linear algebra, and this is lecture number. This is lecture number 70. Okay, so today we will learn another new important topic is called invariant subspaces. Invariant subspace. Okay. Okay, so let us define what do you mean by this invariant subspace formally. So definition. So let V be a vector space over a field F and T be a linear operator on V. Okay. So a subspace W of V is called a T-invariant subspace. It's called a T-invariant subspace. Okay. Subspace. If T of small w belongs to W for all this element of W, for all small w, right? What does that mean? That is image of capital W under T is actually inside capital W. Okay. Then we call W is a T invariant subspace. Okay. Now obviously what are the natural examples? So given any vector space V, so we have always two trivial subspaces. One is the zero subspace, other one is the total subspace B. So they are T invariant for any T, right? Invariant for any linear operator T. This doesn't matter. Okay. Now we can have many other examples. So now let if for given linear operator T belongs to LV, then you have some subspaces. For example, this null space, then say range space, then say eigenspace for some eigenvalue, say C, T. They all are T invariant. And this is not so difficult to check they are T invariant. For example, if you want to check null space is T invariant, so you need to check that if you for any element of null space, T of that element is also inside the null space. And that is obvious, right? So let me just give me a proof. So let say V belongs to say null space of T. That is so V is a null space of T means what? So it is a kernel of it is inside the kernel of T, right? So that means T of V is nothing but 0, right? T of V equal to 0. Now we need to check that T of V is also So what you need to check? You check that this kernel is T invariant, means when you apply any element of T in the kernel, the rest will sit there, right? And that is obvious because for any V, so TV equal to 0, so it is also element of kernel, right? Because 0 belongs to the kernel of any operator. What does that mean? That means it's for all V belongs to null space. So obviously, null space of T is T invariant. Now similarly, you can prove that range space and eigenspaces are T invariant. This is a homework. You can prove it. Okay. So now maybe one more important and some interesting example I can give. For example 3. So you choose a vector space V is polynomial, being a polynomial. Okay. And you choose W is your into R. So what is that? That is space of polynomial of degree less than equal to 2. Okay. So then you check that T of, so you define a map from V to V by derivative. So what does that mean? That means T of the polynomial is mapped to the derivative of the polynomial. Okay. And then it's clear that this T of W is actually inside W, right? Because when you take any element of W, which is a polynomial of degree at most 2, when you differentiate it, degree will be at most 1, right? So this is an element of W. So this is T invariant. There are many examples. Okay, so now with the help of this idea of T invariant, so you will define one more important subspace. So let me define it again properly. Definition. So this is also we can define for any so we call that in the definition of T invariant subspace we did not need the idea of that P is a finite dimensional or not, right? We can be anything. We may not be finite dimensional vector space. Still, it is okay. Now, here also we don't require whether B is finite dimensional or not. So let B be a vector space over a field F, and we choose a linear operator on V and a small I vector inside V. Okay. For some vectors, we choose it. Okay. Now we define what? So we define the define the T cyclic subspace, subspace of V generated by the small vector V is the so it is defined as, okay, so we will define it by this symbol Z, small v and t, and this is what this is actually collection of all such gt of v where g of x is a polynomial. So this means this is element of this polynomial algebra over f. Okay, and this obviously you can easily find out that this is nothing but the span of this vector v tv t square v and so on. I mean, I don't know if this is finite or not, so this is so on. So t, tv, t square v, t cube v. Okay, so by this you can soon go on, and so this will be the basis of this. Okay. Now obviously, I mean, so I need to first prove that this is a subspace, obviously, and that is not so difficult to prove this is a subspace, right? So one can easily prove that that this is not that. So this is TV is subspace. This is homework, you can easily prove it. Subspace of V. Okay, not only that, this is actually T invariant subspace. So this is this, so this is also T invariant. And why so? Because T invariant means what? If you can show that the basis elements are the image of the basis element are inside the space, then you are done, right? Now, if you choose any element, basis elements of the form Ti power j, Ti power v, then if we apply T, then you do Ti plus 1 plus j, right? So as this is true as for any TIV, the image T of Ti of V, again this is over to Ti plus 1 of V is the again element of this cycle subspace, right? So what does that mean? That means the cycle subspace is a T invariant, right? So obvious. And this subspace also obvious, as I told you that obvious 0 belongs to that space, okay? And if you add two things, it will be again element of that space. You multiply by constant, again it will be element of that thing, right? So this property of simple, but it has a very nice property. That what is that property? The property is and that so this property is called that this is some kind of smallest properties there. So what is this property? So so this so let me write down properly. Is the smallest invariant kind of some smallest properties there. So what is that property? Smallest invariant subspace containing V. The vector is V. Okay, so that is what? That is number one. V is T invariant. That we already proved. And number two, if W is a subspace of V, which is T invariant and W contains V, the small vector V, then W also contains Z V of T. Okay, so that's why that means that Z V of T is kind of the smallest among all such T invariant subspace of V, which contains that vectors V. Okay, and the proof is also simple. Already we proved that first part this T invariant. Now to prove that the smallest one, what you need to prove? You need to prove that if okay, so for second part, so let W be a subspace of V, which is T invariant and obviously W contains V. Okay, suppose this is the thing, then we need to show that actually W contains the whole thing, right? And that is obvious because if I choose that any vector, any element, basis element, now for any basis element for any basis vector, say this vector of ZV of T, say Ti of V, we need to show that so we need to show that this is element of W, because, and that is obvious because W is T invariant, right? So this is nothing but, so you can do induction D of Ti minus 1 of V, right, and so on, right? So this will be, so by induction you can prove that this is element of W, because W is T invariant. So as V belongs to W, so T V belongs to W, and so on, T square V, and then Ti V belongs to W. So for every basis element of Z V T, this is an element of W, and hence Z V T itself is a subset of W, right? So this is obvious. So this is subset of, actually subspace of W. Okay. Maybe I can give one more example here. So the similar example what I gave last time. For the example, so you choose that your space is space of polynomial, space of polynomials over R. Okay, and you just want to take this operator on LV. What is the operator? Derivative property of this V equal to yes. Okay. Now you choose your V equal to say x square, a vector. Okay, belongs to V. My question is that what is Z x square comma T? What is this space, right? This is my question. And so the answer is that, so you first check that the basis vector. So you start with V, and then you go to V means x square, and then go to TV means the derivative of that, so that is 2x. Then go to T square V, so this is 2, and then 0, right? So it ends here, right? So this will be the basis vector of Z x square T, and what is the span of this? So the span of this is nothing but actually span of 1 x square. X square, which is nothing but Pt of R. Okay, so that this set x square T in this case is nothing but the polynomial, space of polynomial d less than equal to 2. Okay, this is a simple example. Okay. Yeah, so here maybe I should say that in the case of, okay, so maybe just let me write down that. So when ZV of T equal to, it can be 0 also, like it can be the 0 space also. Okay, for example, if you start with 0 vectors, then it will be right. Now if you start with a non-zero vector, then it is always non-empty, right? But it can be proper subspace, can be full space, right? So when this is full space V, and then the vector small v is called the T cyclic generator of V. Okay, so obviously you can find out whether some and V is called a T-cyclic subspace. Okay, so you can find out whether you have some subgenerator or not, some particular spaces. So whatever vector spaces you have done, try to find out and then start with some operator T, and then find out that whether with this operator you have some cyclic vector or not. Generate V. Okay. Now, okay, so far so good. Now, the natural question one can ask that because T is if you start with the T invariant subspace, okay, so this is natural question. So first let me define it. So so something that T belongs to that operator of V, and W as subspace of B, which is T invariant. Okay, invariant. Suppose this is given to us now, so one can ask naturally that whether we can restrict T on W or not. That is obvious, right? Because T is from V to V, right? And when you restrict T on W, so this will be from W to W, because W is T invariant, right? And this map I am defining by this symbol TW. So what is TW? TW is the restriction of T on W. And fortunately, because W is T invariant, the image of this TW is again inside W. Okay, so this is a linear map. Linearity is coming from the linearity of T itself, right? So one can ask a simple question: what about that? What is the? I mean, do you have some condition that this the characteristic polynomial of this TW that's to some basis uh, and characteristic polynomial of say the full space? What is the relationship between these two things? Are there anything or not? The answer is yes. There are relations between these two things, and this is the theorem. Okay, so so let me start the theorem. So it tells you that so this is I'm taking finding the vector space. Otherwise, you cannot talk about characteristic polynomial, right? So I mean you can talk, but you cannot have a proper result. So let be a finite dimensional vector space over a field F. Okay, suppose this is given to you, and you have linear operator T, linear operator on V, and you know and W say W V a T invariant subspace of V and subspace of V. Then what happens? Then the characteristic polynomial of TW that divides the characteristic polynomial of T. Okay, so then the characteristic polynomial of TW divides the characteristic polynomial of T. Okay, so that means you can have the characteristic polynomial of W that's sitting as a divisor inside the characteristic polynomial of T. So characteristic polynomial of T can be factors into smaller polynomials, and one of the factor will be the characteristic polynomial of TW. Okay. The proof is not so difficult. So you start with the basis. So you first start with the basis. So let say maybe beta 1, something say V1, V2, Vk. This be a basis of W. Okay. Also, I'm assuming V is fine dimensional, right? See. Yes. So what does that mean? That means say something dimension of V is n. So this I'm assuming. And so we have a basis of W of dimension k, and then extend it to a basis say B of the form V1, V2, Vk, and then up to Vn, right? After that k plus 1 to Vn, and this is the basis of V. Okay. So now what happened? There are two bases, right? One is for W and that is for B, right? Now when you restrict TW, T on W, so the map TW, you can talk about the basis with respect to this map, right? So the map, suppose the matrix is B, which is matrix of TW with respect to this basis. Say B1, and this is nothing but Bij, this element of Bij, right? I and J is 1 to K, 1 less than equal to I, less than equal to J, less than equal to K, right? Okay, and what are the relation of that thing? So relation is what? So T of Vj will be summation Vij and Vi. That is relation, and this I equal to 1 to K, right? Uh, now when you now when you're talking about matrix penetration of T with respect to the basis B, then one, so this is with respect to basis B1. Okay. Now suppose you have, okay, maybe you can write down this is B dash, otherwise there are too many B's. Now suppose you want to talk about, so the matrix representation of T with respect to the basis B dash. So let us say that this matrix A, which is of the form Aij. Then what is the relation? Then you know that T Vj equal to summation Aij and Vi, your I is running from 1 to n, right? But note that this W is T invariant. So what does that mean? That means that first this Kevin vectors, when you apply T, it will be again inside W. Okay. So when you write down the image of V1, V2 up to Pk, they will be again linear combination of only V1, V2, Pk. Okay. So when you apply TVJs, right? So this is for anything, but in particular TVJ is equal to summation I equal to 1 to K Aij and Vi. Whenever your j is less than equal to K, okay, then this is the truth. And if j greater than K, then obviously you can have all those things. So what does that mean? So in this case, when j less than equal to K, all the other ij's are 0, right? Other aij's are 0. So you can write down that is plus summation 0 times bi I equal to K plus 1 to n. In the case when j is less than equal to K, in that case, okay. So what does that mean? That means for first K many columns, you have special kind of columns. So in the columns you have some non-zero element, then zeros, right? But the same, the values of T on Vj's are same on WL, right? This is also same value. But here, so what is the difference here? The difference is that these Bij's are then AI, okay. What happened to this? I think, okay. There is a problem here. What is the problem? Okay, so I think we have lost something here. Okay, so no problem. So I think what is the problem? I'm able to understand. I can find out. Okay, so anyway, so let's go to this next page. What is? Okay, so this is. Okay, so you know that the value of the Vj's will be unique, right? So the Bij's are linked to the Aij's also, right? So this is nothing but the Aij's whenever j less than equal to 0 and other thing is 0. So what does that mean? That means if you write down this is a basis form, then B, the matrix B will be Okay, the matrix B will be of the form some matrix, right? So that B11 and so on and BKK, right? K cross K matrix. But inside matrix A, what happened? Inside matrix A, you will have you will be having a nice kind of block. So what is the block? So if you have first K many places, you will have kind of this matrix B is sitting there, right? For first K many places, and that is because of this. That is because of okay this because Kij's are 0 whenever j less than equal to k and I greater than k. For I greater than k is 0, right? So it's kind of upper triangular matrix. The lower part is 0 here. Okay, this portion. So you have 0 0 0 here, and here you can have something else, some matrix, some b1 b2. Okay, it doesn't matter. Okay, so this will be the matrix A, which is a matrix of T with respect to the basis B dash of V, and B is a matrix of TW with respect to the basis B1, right? And now with the help of this, what is the advantage here? So advantage is that you can now find out the characteristic polynomial, and the characteristic polynomial of P will be what, or A, whatever that will be. I mean A you can write down. So this will be nothing but the determinant of xi minus that matrix A, right? But this will be what? This will be, you will have this n plus n matrix, and then you will have here the block matrix kind of B1 and B2 and 0 here, right? Now when you talk about this determinant, so you'll first, in the first place, you'll have a block of xi minus b kind of matrix, and then you'll have xi minus b2 minus b1 and then 0. This kind of block matrix. Determinant of this kind of block matrix, right? Now because of 0, this b1 and this multiplication has no impact, so only impact will be coming from this diagonal portion, right? And hence this characteristic polynomial will be of the form determinant of xi minus b into determinant of whatever x. So this is identity, k cross k identity, and the rest one, this xi will be n minus k cross n minus k, right? The total matrix is n plus n matrix, so this is n minus k cross n minus k minus some b2, right? This is determinant. But this is what? This first portion is nothing but the characteristic polynomial of TW, right? Or B, whatever. And then you have some another polynomial of x, maybe gx. And this shows that this characteristic polynomial of TW, which is a factor inside the characteristic polynomial of T, and hence the characteristic polynomial of TW divides the characteristic polynomial of T. This is a proof. Okay. Okay, so this proof is not so difficult, and maybe I can give an example, and then we will have more better idea, understanding. Say example. Suppose you have a linear map from say R4 to R4. I defined V1, V2, V3, V4, this vector as something say V1 plus V2 plus 2V3 minus V4. First one. Second one is say V2 plus V4. Third one is say 2V3 minus V4, and fourth one is say V3 plus V4. This is a linear map on R4 to R4. Okay, and you want to and you have a subspace say W, which is subspace say generated by two vectors, this 1 0 0 0 and 0 1 0 0. Okay, this is generated by these two vectors. Maybe I can say span by these two vectors. Okay, so these two are linear vectors, and if we generate by these two vectors, then what will be the so W is also generated by these two vectors. Now the question is that whether T invariant or not. That is obvious. So W is T invariant, that we can easily prove. So W is T invariant as what? So you just choose image of T of this vector 1 0 0 0 under the operation, and if you find out that will be nothing but first term will be 1, and then second term will be what? Second term will be nothing but 0. Everything will be 0 other than that, right? You can write down 1 times 1 0 0 0 plus 0 times 0 1 0 0. And what about that other vector 0 1 0 0? So you see that this is actually 1 1 0 0. So this is nothing but 1 times 1 0 0 0 plus 1 times 0 1 0 0 0. So both the images is inside the space generated by the vector 1 0 0 0 and 0 1 0 0, right? That means W is invariant. Now the question is that what I ask you, that what will be, how the matrix look like. So with respect to the basis, so we have chosen a basis here. So basis is what? Basis is this. This is my say B1 of this form, right? Generated by these two things. I can extend it to B or B dash, which is a standard matrix. So this is nothing but, and this is E1, E2, E3, and E4. You remember what are those E1, E2, E3? So here, see, the first one is E1F, second one is E2F, right? Now you can have the elementary standard basis, right? So E3, 4, E3 has 1 as third position, E4 has 1 as the fourth basis, right? If you extend this basis from B1 to B dash of R4, then you can ask the same question, that how this link their characteristic polynomial. Now you check what are the characteristic polynomial of E4 and that. So obviously the matrix representation of TW with respect to the basis, the first basis say B1 will be of the form 1 0 1 1. That way you just calculate. You can also find out that the matrix representation say maybe B2 of T with respect to the basis B dash. I just check it. The first column will be 1 0 0 0 1 1 0 0. That is obvious because it's block diagonal, right? And the next will be what? So next you can check it to 0 to 1, and then it will be minus 1 1 minus 1 1. So this is kind of block diagonal. This is 6, this is 0, right? And so this is clear that from this is clear that if you want to find out the determinant of xi minus b2, that will be contain determinant of xi minus b1, right? Now find out this what is that, their characteristic polynomial. Okay, it's not a problem. Okay, so now I will talk about a very interesting observation. So what is the observation? That the Cycle Subspace actually has a very nice results, and then we will do that. Okay, so let's do this. Next theorem. So next theorem talk about how this T-cycle subspace look like. Okay, so and how the basis look like. Okay, so let theorem. Okay, so similarly let start with the find a vector space. So let V be a finite dimensional vector space over a field F, and you choose T is a linear operator on V, okay, and also you choose a non-zero vectors, and you have a vector V is non-zero element of V, okay, and you also assume that the dimension, let the dimension of this Z Vt is equal to k. Say for example, what does that mean? That means that the T cyclic subspace by V is of k dimensional. Okay, so k means k less than or equal to n. Okay, so I'm also assuming dimension of say V equal to n. Okay, find dimension. Now with the help of this, we can say some things. So first thing is that in this case, say the B, which is V dV and dk minus 1 of V, this forms a basis. This forms a basis of this Z V T. Let me write down say W. Otherwise I have to write down every time Z V T. Okay. And not only that, you can also talk about how the characteristic polynomial of TW look like. Okay, TW means that when you restrict T on W, W means this T set is surplus. So these are coming from something called companion matrix. Okay, so that we will prove that. Okay, so maybe I will prove the next part later. First, let us prove this part. So how do you prove that this is a basis? So that means what? That means this set is also linear independent, and obviously if the dimension is k, then that will be basis, right? Okay, so how do you prove this thing? So for example, if you start with a non-zero vector, singleton will be always basis, right? So proof. Let me start with the proof of this. Proof of 1. So as V is not equal to 0, so the singleton set is linearly independent, okay, over any field, okay, for that field, okay. So now you choose that the largest value of J for which V2 T J minus 1 V will be linearly independent, largest. After that, linearly independent, okay. So let J be the largest positive integer, such that what happened? Such that the set that V TV and up to Tj minus 1 V is linearly independent over F, and that is always possible because J is at least 1, right? Because V singleton is linearly independent, right? So this J is at least 1. J cannot be 0 because if J is equal to 0, so J equal to 1 gives you that singleton V, that is linearly independent. You know that, right? J is at least 1, that you know, but J is also finite because J cannot be infinite. Also J is finite as dimension of V is finite, right? This is finite dimension, something n. And if J is not finite, then you will have infinite sequence of linear independent vectors inside the finite vector space, which is contradiction. So it's not possible. J is always finite. So now So from this definition, what do you know? What you easily can say that. Okay, so maybe let me write down that thing. Okay, so let me write down. So this is a name. This is basis. So up to j minus one, right? So let me give a name. Say maybe this is b dash. Okay, so let this w dash is the space span by b dash, and w was my zvt. Okay, and so suppose w is something some space span by b dash, because b dash I know that this is I chose the maximum j for which these vectors are linearly independent, and any linearly independent vector, if you take the span inside of that becomes the basis, right? So you take that w dash, which is span of this b dash, and then automatically so you know that this w dash is subset of w, this as this so this b, so obviously b dash is inside w, right? Because w contains all the vector of the form tiv for any I, right? So, because this vector is inside w, so w dash is subset of w. That is obvious. Okay. Now on the other hand, on the other hand, and you see that w dash is a t invariant subspace. Okay. On the other hand, uh, this w dash is a t invariant subspace. T invariant subspace of V containing V, right? Containing the small v, right? Why? Because small v belongs to W dash, that is obvious, because the basis element, small v is the basis element of W dash. Okay. But why this even invariant? Because if you apply as for any basis element, say T of uh, L of V is the element of B dash, you have to show that there are two possibilities. Either it is of the form okay, so maybe I let me give a proper proof. Okay, so intuitively you can understand, but I need to give a proper proof. So why this twin varying? So first of all, you check that Tj of V is a element of W dash, as this Tj of V is linearly dependent, because I choose V to j minus 1 of V is the maximum, the largest j's for which this is linearly independent, right? So that means Tj of V is linearly dependent with this basis V dash. Okay, and now you recall that is something linearly dependent. That means this vector is a element of the span of B dash, right? So thus uh, Tj of V is a element of span of B dash, which is W dash. This is obvious, right? Now Tj of V is element of W dash, and you also know that W dash is span of B dash, which is element whose elements of V2 up to V, TV up to T j minus 1 V, right? So what will be the general element of W? So let W belongs to, or rather W belongs to W dash. Then you can write down that that W dash will be something, say alpha 0 V plus alpha 1 TV and so on, right? And alpha j minus 1 T j minus 1. What happened? Yeah, So here j minus 1 of v, right? This will be of the form because basis vector of w dash will be v t v t j minus 1 of v, right? And this alpha is our element of field, scalar field. Okay. So then t, what is the value of tw? Tw will be nothing but alpha 0 tv and so on. And the last vector will be c alpha j minus 1 t of j of v. Now before tj, everything will be element of a basis vector w dash v, right? And tj of v is also element of w dash. I just prove it here. Here, see. So what does that mean? That means this is a combination of every element of w dash, and hence this is the element of w dash. So what does that mean? That means any general element of w dash is also element of w dash. And done. So this proves that w dash is T invariant, and w dash also contains v. Now recall the property of cyclic subspace. T cycle subspace, it is kind of minimal one, right? So what does that mean? That means this minimal means that w, which is z v t, which is actually subset of w dash, because w dash contains v and also this t invariant, hence this is this. And also otherwise is obvious, so this implies that w equals w dash. Okay. So what does that mean? That means they are the same. So that means that b is nothing but b dash and j equal to k. Okay. This is a proof actually. So that proves that v tv and t k minus 1 v is forms a linear independent vectors of k dimensional vector space w, and hence this is the basis of w, right? This is a proof. Okay, and next what is important that I need to also show that you can also talk about the characteristic polynomial of tw. How? So you start. You know that tv tk of v. So okay. So next. So as say tk of v belongs to w. Okay, because this is linear dependent, right? And so this is span of that thing. Okay. So this element of w, which is linearly dependent of. So the w, and w is span of b, and b, you recall b has element v2 t k minus 1 of v, right? So there exists some constants c0, c1 to ck minus 1, such that what happened? As I write down that c0 v plus c1 tv dot 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 ck minus 1 of tk minus 1 of v plus tk of v equal to 0 easily. Or you can say that this will be minus of that. I wrote intentionally plus to get some nice form. Okay, and if this is the condition, then what will be tw matrix form tw with respect to this basis. Tw not tb. What will be matrix form tw with respect to the basis b, and now you can easily find out it. Why? Because you see that when you apply t on v, it will be v, right? So let me write down that. So t on v, which will be tv. So this is nothing but 0 into v plus 1 into tv and 0 into t square v and so on, right? Similarly, you can write down every element t of vi, t of ti of v. T of v, this is a basis vector. This will be ti plus 1 of v, right? I plus 1 of v. Okay, so what will be the matrix then? The matrix will be of the form it is 0 and then 1 and 0 0 0, similarly 0 0 1 and 0 0 0. Kind of sub diagonal is all 1. Sub diagonal means diagonals, subdiagonal means that exactly one below the diagonal. Super diagonal means one above the diagonals. Okay, except the last columns. Last column, what happened? Last column you'll have um, TKV, right? So when you apply T on TK minus 1 of B, you will have TKV, but TKV will be minus of all those vectors, right? Is that okay? So T when you apply on the basis vector TK minus V, it will be TKV. But TKV will be nothing but minus of that Ci uh, Ti of V I equal to 0 to K minus 1, right? So this will be minus C0, then minus C1 and minus Ck minus 1, exactly. This is the matrix forms of TW. But then what is that characteristics polynomial? So characteristic polynomial will be exactly, so this is kind of matrix called companion matrix, and the characteristic polynomial of TW will be exactly, now we find out that it will be nothing but C0 plus C1 of x dot 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 Ck minus 1 of x power k minus 1, and last one is C power x power k. So this will be the characteristic polynomial, which is obviously a harmonic polynomial. Okay, and this C0, C1, C2 is actually sitting as a last column. Okay, clear. So this is a nice way of telling how these exercises look like, and this is going to help us to prove one of the major important theorem, which is called um, Kelly-Hinton theorem, and that we will do in our next lecture. Okay. Okay. So today I will stop here.